All right, so last time we talked about disjoint unions, quotients, and pushouts. So the first half, 3/4 of today will just be examples of topological spaces constructed using these methods. A few people have asked me, well, I get the feeling that you guys were all with me up until we started topological spaces, and then it's like the bandwagon was just like, poof. Okay, that's... So partly I can try and fix that by saying some words, so I'll do that. Partly that's just, it is an abstract thing, right? And it's just, you've got to grapple with it. There's sort of an irreducible complexity to getting over the idea of topological spaces, which I can't really do for you, I think. So you'll just have to wade through the material, and I promise you, if you put in the effort, you'll get some grasp of what a topological space is. But maybe the following is helpful in the interim. So we've, what topological spaces do we know? Well, basically, what we've discussed, at least to begin with, was taking a metric space and getting a topological space out of it. So what does that mean, really? It means you take your metric space and you just remember all the open balls. Right? That's what you did. But you forgot the distance. So you remember the balls, but you don't remember their radius. If you remembered the radius, the radii, of all the open balls, you would have remembered the metric. Okay? So you took all the open balls and you just forgot their radius. That's what you did by going to the topological space. So if you don't find that too exotic, then actually that's, most of the content of the theory of topological spaces is just the observation that you can make do with just a collection of open balls, and you don't really need to remember their radii for many purposes. Okay. Now, not all topological spaces arise in this way. We discussed the Sierpinski space. Those are genuinely the harder things to sort of get your head around. I won't say too much about this. I think that's just a matter of experience, but it's a little bit analogous to the situation with complex analysis versus contour integrals, right? So you may have had complex analysis motivated to you for the following purpose, right? Okay, I want to do this integral. Oh no, I cannot do it. Okay, but complex numbers to the rescue, right? Then you learned about contour integrals, and that was easy. Now, what is the deep significance of the imaginary number I to that problem? Well, there's a long story involved in that, but from one point of view, this extra stuff, so this enlargement of my number system, just allowed me to talk about the things I already cared about, just in a more convenient way and a more powerful way. Now, you will be safe, at least for the moment, if you think about topological spaces in just that way. So even if you only care about metric spaces, it is convenient to have around these extra topological spaces which are not metrizable, because they give you a powerful language to prove deep theorems about the things maybe you started off caring about. And then through some process, you end up magically caring about complex numbers somehow, right? So, okay, that's the same thing here. That's the pitch anyway. All right, so many topological spaces of interest are metrizable. That is, they come from a metric. But maybe they come from multiple metrics. Okay, so another way to think about topological spaces is you're working with metric spaces up to this equivalence, that is, up to them having the same system of open balls, sort of roughly speaking. So for instance, as we'll discuss in the tutorial, so these three metrics, we didn't say much about them, but so D1, D2, and D infinity, they all induce the same topology on Rn. And for many purposes, who cares what the actual distances are, right? You just care about the structure of Rn as a topological space. You could frame everything you wanted to say in terms of these metrics, but it's like carrying around this extra baggage that's not really relevant, right? So working with the topological space is a way of working with Rn without having to care particularly about which metric gave rise to the topology. Okay, was there anything else I wanted to say? Oh yeah, so these are natural things that we would imagine doing with spaces, right? So for instance, if I give you the topological space, which is the interval, well, you certainly have in your head some consonance with the idea of taking two intervals and just thinking of them both at the same time, right? That doesn't seem like anything too crazy. And we can do that as topological spaces. That was easy. But if I wanted to think about that as a metric space, and I can, it's certainly metrizable, I mean, what do I have to do? It's not very dignified, right? I sort of have to, I have to figure out what is the distance between this 0 and that 0. Well, it can't be 0, because then they'd be the same point in a metric space. So I have to invent some number. It has no real significance. I just need to pick a number, right? So I could take, if this was R2, I could sit the intervals inside R2 somehow, and then, well, I would have 2 copies of the interval with the subspace metric. That would be a metric space structure on the disjoint union. But OK, so then there's some number here which is the distance between 0 and the other copy of 0, and between 1 and the other copy of 1, and it's just kind of random, right? Who believes in that metric? It's meaningless, right? So I can think about that as a metric space, but it's sort of a bit silly. So I work directly with a topological space, which is what I'd get out of that if I did put a metric on it. But that has a canonical sort of nature, whereas this, I mean, one can be a bit more clever about putting a metric on the disjoint union, but you sort of get the message. And the same thing with the quotient. You can put, well, in general, actually, I don't think you can. But in some cases, for some equivalence relations, you could start with a metric space X and an equivalence relation and put a metric on this such that you had a map which preserved distances from X to the quotient. But it's, you look at it and you're just like, I don't want to do that. Okay. Whereas, I mean, maybe you don't want to do the version with topological spaces either, but I claim you do. Okay. So putting the equivalence relation and taking this quotient topology was this totally natural thing to do with topological spaces. So that's the sense in which topological spaces are useful. And OK, so I think that's enough about that. OK, so I said I'm going to talk about examples. All right. Well, the examples are going to come along with some observations and some exercises for which I need to finally give the following definition. So a continuous map f from x to y is a homeomorphism if there is a continuous map going the other way with the composites in both directions are equal to identities. But that's equivalent to saying f is a bijection and the inverse function is continuous. Right? That's the same statement. It's not the same. I mean, you may be used to a situation with, say, groups where a homomorphism of groups was an isomorphism if and only if it was a bijection. Right? That's not true here. So it's certainly possible for a continuous map to be a bijection, but not a homeomorphism. Right? So it's sort of easy to see that f will be a homeomorphism, well, if and only if f is bijective and f is called open, which is to say if u is open whenever u is open. And if you think about it, saying that f sends open sets to open sets in that way is precisely the statement that the inverse function is continuous. Okay. So that's a homeomorphism, and that's the notion, the appropriate notion of two spaces being the same. If two spaces are homeomorphic, it's silly to distinguish them. They're really the same space. Okay, so example. Okay, so let's just take the interval with the usual subspace topology of R, if you like, or the metric topology. It's the same thing. And I take the equivalence relation, which is generated by a single pair, which identifies 0 with 1. Right? So the actual equivalence relation, of course, contains the pairs like lambda comma lambda for every lambda between 0 and 1 and not equal to either of them. So this is the generating pair. So that's a topological space, a quotient space, according to what we said last time. So by the way, if a homeomorphism from x to y exists, we write and I might say x is isomorphic to y. Isomorphic and homeomorphic have the same meaning for the moment anyway. Okay, and I say x and y are homeomorphic. All right, so exercise prove this x is homeomorphic to the usual topological space S1. Okay, so you get to pick which way you want to write down the map. And if you think about it, it's sort of natural to map x to S1, right? Because what's a map? If I took any topological space Y, and I think about to define a continuous map out of the quotient space, well, the whole point of setting up the quotient space in the way I did it last lecture was that we know exactly what those continuous maps are. Those are in bijection with the continuous maps from 0, 1 to Y, such that f of 0 is equal to f of 1. Right? This here was the so-called universal property of the quotient. It's the way I set up the quotient space. So if I want to talk about maps out of the quotient, they're exactly continuous maps out of the numerator, which send everything that's equivalent under the equivalence relation to the same point in Y in this case. Okay, so to give a homeomorphism here, I just have to write down a continuous map from the unit interval to S1 in this case, which agrees on 0 and 1. I think you can think of such a map. Then you need to prove it's bijective, and you need to prove that its inverse is continuous. Okay, but that's, as I said, so that's an exercise. Okay, so that's a homeomorphism between S1 and this quotient space. Now let me do an example, which is a pushout. Any questions about that one? I mean, of course, they feel a bit different maybe, S1 and this interval where I just sort of force the endpoints to be the same. But you're thinking about like an embedding in the plane or a metric or something. So, you know, I don't have to curl it around or anything, right? I just declare them to be the same. And then there's no embedding in the plane that needs to be taken care of to bend them around, right? It's just, as a topological space, they're the same. That is, there's a bijection of the points which matches up, if you like, the open balls. I mean, not with the radii of an open ball going to an open ball, but sort of neighborhoods which are unions of open balls match up. So as long as the locality of points and what's in what neighborhood matches up, they're the same topological space. There's no embedding in the plane or something that needs to be taken care of. So they're genuinely the same topological space. And again, have a think about how you would do that as a metric space, right? If you wanted to take that quotient. Sort of a bit strange, right? You can't set points anyway. Okay, so. All right, so we're going to construct a space by a pushout. So whenever I write this thing, I just mean the space with one point and the only topology that's possible on that. And if I take that disjoint union, well, then it's two copies of this point. So let's call them star 1 and star 2. Well, there's only one function in the numerator, so let me not give it a name. And f is just the map that sends one of the copies of star to 0 and the other copy of star to 1. Okay, so what's that pushout? Well, remember the pushout was by definition the disjoint union modulo an equivalence relation. The equivalence relation gave us one generating pair for every point here, right? So I'll get two equivalences, one for star 1. The equivalence relation, well, the relation for star 1 says star 1 going to here, that is the star there, has to be identified with wherever star 1 goes here, which is 0. And the equivalence relation I get by taking star 2 is 1 is equivalent. Okay, so this was not, in fact, a new example, right? Because what did I do? I took, the space here was I took star and I added on as a disjoint union an interval. Okay, so I'm drawing this in the board, but don't think of this as embedded anywhere, right? This is just sort of sitting free of any embedding as a set. And then I identified star both with 0 and with 1, but in particular 0 was identified with 1. So this guy is just, again, the same space. Right? So there's a homeomorphism. Well, this is the equivalence relation from the previous example, and again, that's S1. Okay, so those were two ways of constructing the same space. Oh yes, go.
Hi Daniel. So I just want to clarify this. So it feels like a quotient space and a pushout are kind of almost the same thing.
That's right, yeah.
So is a pushout just a way of writing an equivalence relation in kind of a more natural way, or is it something different?
Yeah, so from the way it's defined, it's made up of these two pieces, a disjoint union and equivalence relation. You're right. So the pushout is really just a way of describing the equivalence relation. Yeah, that's it. So it's just a way of packaging the equivalence relation. But the quotient space is more general, if you like. So you could have a very complicated, so this is a particular kind of relation which is always of the form, so pushout always has this kind of.
And you could have more general questions.
Yeah, that's right. So the pushout, well, it sort of has these two stages, one of which is, so you've got two spaces, you're supposed to take their disjoint union, and then you're supposed to stick them together somehow. And the way they're stuck together is, if you like, think about y over here and z here, and then there's some piece of those which is in common, so to speak. I mean, suppose f and g are injective. Doesn't have to be, but often they are. So if f and g are injective, then you've got some subspace of both y and z, which is x. And then we're sort of sticking y and z together along that common piece. So that's the pushout. Yeah. But if you want to think about it as just a bookkeeping device for what the equivalence relation is, that's also completely accurate. Yeah. Yes?
In this example, you basically said that 3 points pointing towards lines is basically a circle. Is that what?
Yeah, that's, no, not quite, because, yeah, thanks for the question, though. So that's why I'm using a different color.
Okay.
Yeah, that's not very clear, I suppose. But so read this line as not a line, but an equality sign that's just sort of stretched out. Okay, red means equal. Yeah, so star is equal to 0, and star is also equal to 1. So I could, if you like, have drawn this example with the same convention in this way. So there's 0, there's 1, and they are declared equal, but I'm not inserting another interval, if you know what I mean.
I mean, you could, and it's sort of a
Yeah, the trouble with this example is I could, and it wouldn't have changed anything. Yeah, that's right. So I guess this should be red too. Yeah.
That last example we did there, could you use like a similar push-out setup to sort of define boundaries of manifolds?
To define boundary, yeah, I mean this. This is indeed how manifolds are often glued. Yeah, I mean that's a good example. Yeah, maybe I'll do an example like that now. That's a good one. So maybe I'll do this one sort of more pictorially. So let y be this space. Often called a pair of pants. Literally. So what is that picture meant to be? Well, I don't want to describe it as a set with some equations or something, because that would be horrible, but you get the idea, right? So I take a subset of R3 that looks like the surface here. This is not meant to be a solid object. It's a sort of two-dimensional it's a two-dimensional surface, so I've got the bits I'm coloring in. There's the bit at the end is not filled in, right? So there's a circle sitting inside y there, and the bits interpolating between, I mean, it's not convex around that circle, and the inside is missing as well. Okay, so I think that hopefully specifies the surface. Well, I just drew a circle, so let's call that circle S1, and let's call that map that puts S1 inside y F, right? So okay, so that's F. Let's also consider Z, which is, let's say, I don't know. So again, a surface. Okay, there's some hole taken out of the middle of it. If you like, this is y stuck together with itself going around the other way. Right? Anyway, it's not very important what it is. Then there's another map from S1 to Z, which sits the circle in as that boundary. Right? So the boundary, we haven't defined boundaries. We'll do it in a little bit. But I think it's sort of clear intuitively. The boundary of this manifold Z is the union of two circles. Here it's a union of three circles. Okay, so you can imagine the map G, which sits that circle inside that endpoint. And then I can write down the following pushout diagram. Right, to form a pushout, I need two maps out of the same space. And what is the pushout going to do? Well, it's going to take the disjoint union of y and z, and then it's going to, the equivalence relation is going to say for every point in S1, identify the image under F with the image under G of that point. Right? So that was X, that was Fx, that was Gx, and this equivalence relation is made up of things that look like Fx, Gx, where x is in S1. Okay, so I've got to glue that guy to that guy, and then I've got to glue this guy to that guy, and all the way around the circle, so they've been completely identified. And so the thing I'm left with as the pushout is just the picture which first does Z, and then does y, and there's no line in the middle anymore. All right, so that's the, and if you like, and you can still recover that circle because it's the image of the S1 going to here, going to there, right? That's that red circle, and it's the same either way. That's the whole point. Yeah, so that's another example of a pushout. Maybe the pictures make that a bit clearer. Is that what you were getting at? Okay. All right, any more questions about the pushout? All right, so So I think that example sort of covers a lot of the ideas. So maybe I'll quickly, so there's several ways of defining the torus, usually denoted T. One is to just take the product of two copies of S1 with itself. Now, the way you're supposed to think about the torus is as this picture, right, embedded in R3.
Once again, is that the surface?
That's a surface, yeah, that's right. So what's the connection between that description as a product and that picture? Well, the elements here look like S1 cross theta. So I can take the union over all thetas of S1 cross theta and get that Cartesian product, right? So it's one copy of the circle per angle. Well, that's just what I drew, right? Because think about the plane sort of cutting this bagel in half, and then for every choice of the angle, then I get a copy of the circle, which is the slice sort of going outwards from the origin through the bagel, so to speak. Right? So for every theta, I get a copy of S1. And the union over all of those takes me all the way around the torus. And the topology that I mean, that's as a set, right? So I convinced you it's the same picture as a set. And the topology, if you think about what the product topology is saying, matches up with, well, I mean, as an exercise, find another description of the torus as a subset of R3, put the metric topology on it, and you can check that that's homeomorphic to this Cartesian product of S1 with itself. And there's another description here in terms of a gluing. Maybe I'll leave that. Okay, so example. So I think you've all seen this at some point. Okay, so this is sort of easy to describe informally, right? So take 0, 1 cross 0, 1. Think about that sitting in the plane. And then I'm going to glue two of the opposing edges together. Well, one way to glue this thing together would be to I glue that edge to that edge, matching up, say, that point to that point. And I also glue that edge to that edge, matching up the points as they are indicated. If I did all that gluing, I would get the torus. All right? So that's a useful exercise, right? Because that tells you there's a surjective continuous map from 0, 1 cross 0, 1, which I write as 0, 1 squared, to the torus, right? Because there's a surjective continuous map from any space to the quotient space. Okay, so the torus is a quotient space of the unit sort of square. But I don't do that gluing to get the Mobius band. I leave the top and bottom alone, and I glue the left and right to each other, but in opposite order, and these two arrows that I just drew are explained by the following set of generating pairs for the equivalence relation. So that's 0, 1. And what I do is I take the left-hand boundary, let's say 0 lambda. So this is for all lambda between 0 and 1. And I identify it with 0, 1 minus lambda. All right, so a point down here is identified with a point. Oh, thank you. Yes. Okay, so that's a generating set of pairs for an equivalence relation, and M, the Mobius band, is 0, 1 squared and mod that equivalence relation. And, well, there's a picture in the notes. I won't embarrass myself by trying to get it correct on the board right now. You know the story, right? It's twist and put. Okay, so that's an interesting example of a surface. All right, so those are a few examples. Any other questions so far?
Equivalence relation had to be linear, like one had to be 1 minus lambda rather than.
Yeah, no particular significance about that. No particular significance about that. Yeah, I mean, yeah. It's a good question though. So take any monotonic increasing continuous function, and then check that what you get is homeomorphic. I should be careful when I say that, but I think that's going to be correct. Yeah, that's right. So then there'll just be a local reparameterization. So that's going to be a bit tedious to check perhaps, but that's probably true. So there's no real significance about the linearity. Yeah. All right, so I mean, you can see, sort of get the idea, right? Then basically anything that you can sort of imagine gluing together basic pieces, you can probably implement using these tools. I'll discuss CW complexes in a second, which is the sort of fancier way of making sense of what I just said. But before we get to that, let's observe that this sort of zoo of constructions then raises the obvious question, which is, well, when are two things that I construct this, like using two different methods, for instance, I mean, when are they the same? So we've already seen several constructions of the torus, several constructions of the circle, and then, so the general question is, okay, so if I'm given two topological spaces, I mean, what does that mean? It means I'm given a set and a topology, right? Or maybe I'm given a construction, if you like, a kind of algorithm to build it, as you are in these cases. But even if you have the algorithm to build it out of simple pieces, it's by no means obvious always whether what you've got is the same space as some other construction that produced the space, right? So this is actually a very hard question. Are two given spaces homeomorphic? So I'll take some examples from the list we've already constructed. So what about this, for instance? So the Mobius band was where I if I just took these edges and identified them without any business with 1 minus lambda. So if this was just 0 lambda, 1 comma lambda, that would be taking this sort of strip of paper, if you like, and just sticking it together in the natural way. So that would be S1 copies of the unit interval, right, stretched around a circle. But I didn't do that, or at least I didn't think I did that. At least that wasn't what I wrote down, right? I twisted one end of the piece of paper and then stuck it together. So that seems like a different space, right? So I expect the answer there to be no. But the question is, how do you prove that? Well, okay, now I am going to try and draw this thing. Surely it's possible. I'll just try very hard to copy the one I labored over. All right, it's not so bad. So the image of this gluing site, let's say it's there. So that's this piece of paper. So that's a surface. The torus is not the same as the circle. There's various ways of doing that. I mean, again, a lot of the answers to these questions lie outside the scope of the course, but I think it's worth mentioning. So in this case, one of the clear reasons why is that there are circles you can draw on the torus which can't be shrunk down to points. Right? Take your torus, just sort of wrap a band around it. There's no way of deforming that, crushing it down to a point, which is a sort of continuous operation, without going outside the surface. So that's what's called a homology cycle. So the torus has such a thing, but otherwise this seemed a bit silly, I guess. So that's the sphere, right? but the surface of the sphere. Any circle I draw on the surface of the sphere, it's kind of clear I can just pull it around and contract it down to nothing. Okay, so one can make all this precise, and that's one proof. There are probably easier ones that show that the torus is not homeomorphic to the two-sphere. So that's the sort of game that one plays. So so S1 is not homeomorphic to R. We'll see that because S1 is what's called compact, but R is not. The one that's sort of really annoying, well, I mean, this question is annoying. Well, okay, I should say M is not equal to N, I suppose. If N is 1 and M is 2, you should be able to see why this is the case. This is the case where you can actually, without any additional tools, see that this is the case. But for, say, N3 and M4, it's not immediately obvious that these two are not homeomorphic. I mean, they certainly, you don't want them to be, right? But topological spaces are a little weird that way, so that involves a little bit of effort. Okay, but it's not true. So Rn and Rm really aren't homeomorphic when n is not equal to m. Okay. All right, so all the constructions we've done so far, with the exception of this one, fall into a broader pattern. So recall this inclusion of the n-1 sphere as the boundary of the n disk. So, well, I defined them last time. So I discussed making a topological space out of a graph last time using pushouts. So this thing is called the n disk, or sometimes an n cell. All right, those are synonymous. So the point of this definition is it gives us a way of constructing many spaces in an iterative fashion. Okay. Well, why do we want to do that? Well, I've given you some hint already that it may be difficult to tell apart two spaces x and y in general. To actually tell them apart, you need to compute invariance. So an invariant is a quantity like a number or a topological space, which is associated to or a vector space, which is associated to a topological space. So you want to compute invariance, like how many genuinely different sort of circles like that sit inside your torus. And in the torus, there's two. There's essentially only two really different circles that you can embed into the torus. That's one. And there's another one which sort of goes around the whole. Okay, so the fancy statement is that the homology group of the torus, the first homology group, is two-dimensional. It's spanned by these two disks. Okay, so you want to do things like that. You want to look at your space and figure out some simple information about it that you can actually compute in order to distinguish spaces. Well, that means you need to compute something from your space. How are you going to actually do that? Well, you need to be able to present your space often as some sort of iterative construction out of simpler pieces. And that's the reason why the following class of spaces are central in topology. So a topological space Y is obtained from X by attaching n cells So the picture here Here's X. I want to glue in, say, so D1, for instance, is a disk, right, with the interior filled in. Suppose I want to attach a disk to X. So think about taking the boundary of the disk and gluing it into X somewhere, right? So there's maybe where I'm going to glue it onto, and the result of that gluing will be X with some extra sort of appendage. Right? That's the result of taking a disk and gluing it into X. So I have to tell you where to glue it. Well, the instruction of where to glue it is a map from the boundary. That's the thing I'm going to glue. In this case, S1. Right? So that's a copy of D2 that's been D2. Remember, the number here is the dimension. It's a two-dimensional disk. To glue in a disk, I need to tell you where the boundary is going to go, and that's what these maps F are doing in the case n equals 2. Okay, so I have the boundary, which is where I'm going to perform the gluing. That's the attaching map. And then I've got the circle sitting into the boundary of D2, and that pair is the thing I'm going to push out to attach the disk. Okay, so I think in terms of the picture, it's sort of straightforward. It's easy to get lost in the pushouts and stuff, however, right? Okay, so take a family of continuous maps, which are these attaching maps. It could be infinitely many. And if y is the result of pushing out all those maps, right, so take the disjoint union indexed by all the attaching maps of copies of S n-1, the n-1 sphere. So let's again just label the copy corresponding to alpha with a subscript. And well, this is the disjoint union. If I restrict F to any part of that disjoint union, what I'm supposed to get is F alpha. Right? That's defining this map F. And by construction out of the disjoint union, that's continuous. And here I put, again, a disjoint union of copies of the n disk. And then this map here, let's just call it the disjoint union of the iotas. So this is the map which, when restricted to the copy of the n-1 sphere corresponding to alpha, is just the inclusion of that copy into the copy of the n disk labeled by alpha. So that gives you a continuous map. And then if there's a pushout diagram like that, by which I mean that the space y is homeomorphic to the pushout, then we say y is obtained from X by attaching n cells. Okay, so I've got all these attaching maps, and then I do perform all the gluings, and the result is the space y. Okay, so and the definition we're leading to is a space which is obtained by an iterative process of that kind. So a space is called a finite CW complex. There's a sequence of spaces, x0, x1, ... So leading up to x after some finitely many steps, where x0 is a finite set with the discrete topology. Okay, so that's the first step of the construction. And that's just like we did with the graph yesterday, right? So x0 is some finite number of points. And then each of the stages is obtained from the previous one by attaching cells of the dimension which is appropriate to that stage of the construction. So you start with points, you attach lines, to the result of that you attach disks, to the result of that you attach 3 disks, to the result of that you attach 4 disks, and so on. Okay? So for 1 between I and n, xi is obtained from xi minus 1 by attaching finitely many I cells in that precise sense. Right? So finitely many meaning the capital lambda there, the index set is finite. Right? So x1 would be the result of taking some finite union of intervals and gluing them in, which should have the result of making something that looks like a graph. Right? That would be x1. So x1 is the result of the gluing, so it looks like that. And then to form x2, I would take the disjoint union of this with a bunch of disks. And then I would have attaching maps that tell me how to glue the disks. Right? So the attaching maps would be maps from the circle into a space like x1. Well, maybe it collapses the whole circle down to just an edge. Or maybe it maps the circle into something that looks like that in the graph, so a cycle in the graph. Okay, so maybe let's do 2. So suppose I have 2 attaching maps. I'm just gluing in 2 disks. What would the result look like? So the result of gluing in those 2 disks would be here. You sort of imagine you've taken the disk and you've just crushed the whole boundary of it down into a line. So there's sort of a disk. I mean, it's sort of a little hard to draw. It's such a thing that if you collapse that edge down to nothing, what you'd be left with is a sphere, right? If I took a disk and I collapsed the entire boundary down to a point, what I'm left with is something homeomorphic to a sphere. Okay, so that would be another example. Suppose there's just a vertex left over there with no edges attached to it, and I had a map from the circle which sent the entire circle to that point, and then I performed the gluing. What I'd get is a little sphere sort of attached to that point. And here, well, I'd actually fill in a disk, right? Because I've glued in the circle in that way. Okay, so that would be x2, and then I'd have maps from that's the 2 disk, and then I'd have, well, that's the 1 sphere, then I have maps from the 2 sphere into that, and I'd perform more gluing, and I'd keep going until I get down to xn. Okay, so very many spaces which have been prescribed in the way we've been doing in this lecture can be constructed in this fashion. For the moment, maybe that looks a bit complicated, but the advantage is that in analyzing spaces which have this kind of presentation, we can proceed step by step, and it actually makes it feasible to study these spaces.